Hey everyone, welcome back to your channel name. Have you ever wondered how stars the size of entire solar systems come to exist? Today, we're diving into one of the most thrilling discoveries from NASA's James Webb Space Telescope. It has unlocked incredible secrets about Westerlund 1, a dense star cluster home to some of the largest and most enigmatic stars in the galaxy. If you love space, science, and mind-blowing discoveries, stick around because you won't want to miss this. Deep within the heart of the Milky Way lies a dazzling celestial treasure, Westerlund 1, one of the largest and most vibrant star clusters in our galaxy. This cosmic hub is bursting with colossal and luminous stars, making it a spectacular sight of astronomical activity. Recently, the James Webb Space Telescope turned its powerful gaze toward Westerlund 1, revealing groundbreaking details about this remarkable cluster, its extraordinary stars, and the dynamic forces that shape their lives. In this video, we'll dive into these exciting discoveries and uncover why Westerlund 1 holds the key to some of the universe's most profound mysteries. Located about 13,800 light-years away in the constellation Era, Westerlund 1 was first discovered in 1961 by Swedish astronomer Bengt Westerlund. It quickly captured the attention of astronomers due to its enormous mass and unique stellar population. The cluster is a true giant, weighing in at an estimated 50,000 to 100,000 times the mass of our Sun, making it one of the Milky Way's most massive and luminous star clusters. Westerlund 1 is no ordinary star cluster. It's classified as a superstar cluster, a rare and extraordinary type. Its residents include some of the galaxy's most extreme and energetic stars, such as red supergiants, yellow hypergiants, and Wolf-Rayet stars, all known for their immense size and fiery brilliance. In the coming moments, we'll explore how these colossal stars evolve, interact, and shape the cosmic environment around them. Join us as we unravel the secrets of Westerlund 1 and its role in decoding the mysteries of our universe. Westerlund 1 isn't just a star cluster, it's a vibrant hub of stellar drama. Estimated to be 5 to 10 million years old, it's in a critical phase of evolution. Many of its stars are undergoing rapid changes or nearing the spectacular ends of their lifetimes. One of the cluster's most astonishing residents is Westerlund 126, a red supergiant so massive that if placed in our solar system, its outer layers would stretch beyond Jupiter's orbit. These rare cosmic giants provide a unique opportunity for astronomers to study the life cycles of some of the most extraordinary stars in the universe. Another remarkable feature of Westerlund 1 is its extreme density. Packed into a region just 3.26 light-years across, tens of thousands of stars crowd together in an intense gravitational dance. This close proximity creates powerful interactions, shaping how the stars move, evolve, and even influence each other's fates. But the significance of Westerlund 1 goes beyond its own stellar inhabitants. Massive clusters like this are considered the cradles of star and planet formation. As its most massive stars reach the end of their lives in spectacular supernova explosions, they release heavy elements carbon, oxygen, iron, and more into the surrounding space. These elements are the building blocks of planets, life, and the universe as we know it. Westerlund 1 isn't just a star cluster. It's a living laboratory offering invaluable insights into the life cycles of stars and the fundamental processes that shape the cosmos. Westerlund 1 isn't just shaping its stars, it's helping to shape our understanding of the galaxy itself. This extraordinary cluster provides a bridge between the Milky Way's ancient past and its present-day state, offering astronomers a rare glimpse into how galaxies evolve over billions of years. Thanks to the cutting-edge capabilities of the James Webb Space Telescope, particularly its near-infrared camera, NIRCom, and mid-infrared instrument, MIRI scientists were able to peer through the dust that normally obscures Westerlund 1. What they found was nothing short of breathtaking. One discovery was a diffuse nebulosity surrounding the cluster's core. This faint, cloud-like structure, made of intricate droplet-like formations, interacts with the cluster's massive stars. These features are shaped by the intense radiation and powerful stellar winds emitted by these colossal stars. These interactions provide invaluable clues about how massive stars influence their environments, shaping the distribution and movement of gas and dust around them. Another incredible feature was a trunk-like filament stretching approximately 3.3 light-years toward the cluster's center. This elongated structure appears to be a channel of gas and dust being drawn inward by the cluster's immense gravitational pull. This material could eventually ignite new waves of star formation, making Westerlund a dynamic site of creation and transformation. Beyond its visual beauty, Westerlund 1 is a laboratory for studying the fundamental processes that govern our universe. From the formation of planets to the birth of new stars, this cluster holds answers to some of the biggest questions about the origins and evolution of galaxies. Westerlund 1 is more than just a star cluster. It's a cosmic workshop showcasing the dynamic and ongoing process of star formation. One of its most fascinating features is the recently discovered trunk-like filament, a channel of gas and dust being drawn into the cluster. This discovery sheds light on how material flows into massive clusters, fueling their growth and evolution. The James Webb Space Telescope also revealed extended shells surrounding several M-type supergiant stars in the cluster. These shells, varying in shape, offer a glimpse into the late stages of these massive stars' lives. Some shells are elongated, pointing outward from the cluster center, while others exhibit narrow, jet-like outflows. These intriguing structures are thought to result from intense mass loss driven by powerful stellar winds. Observing these features provides critical insights into how massive stars shed material before they end their lives in spectacular supernova explosions. The structure of Westerlund 1 reveals how gravity masterfully channels material into star clusters, fueling the birth of new stars. This discovery refines our understanding of how stars form, especially in dense regions filled with gas and dust. But Westerlund 1 isn't just a local phenomenon. It acts as a nearby laboratory for studying starburst regions similar to those in distant galaxies, which are far harder to observe. By examining this cluster, astronomers can unlock the secrets of massive stars like red supergiants and Wolf-Rayet stars, celestial powerhouses that enrich the galaxy with heavy elements such as carbon, oxygen, and iron. These elements, essential for planets and life, are dispersed into space as these stars lose mass and eventually end their lives in brilliant supernova explosions. Westerlund 1 also provides a rare glimpse into the dynamics of densely packed star clusters, where intense gravitational interactions dictate the motion and ultimate fates of individual stars. These observations are key to understanding how massive star clusters evolve and how they shape the structure of entire galaxies over time. Through the groundbreaking capabilities of the James Webb Space Telescope, Westerlund 1 has become a cosmic gateway, offering profound insights into the processes that govern our galaxy and the universe beyond. Westerlund 1, often referred to as a stellar city, is a young supercluster of stars located about 15,000 light-years away in the Milky Way. What makes it extraordinary is its population of hypergiants and supergiants, stars so massive they challenge our understanding of physics. Many of these stars are over 100 times the size of our Sun and millions of times brighter. Despite being relatively young at just a few million years, this cluster has already begun to shape our galaxy in profound ways. Thanks to Webb's infrared capabilities, we can now observe these celestial giants in ways never possible before. Using its infrared vision, the Webb telescope has pierced through the thick layers of dust and gas surrounding Westerlund 1. What it revealed was astonishing, an unprecedented level of detail about the cluster's structure and the individual stars. Scientists have identified massive amounts of material ejected by these stars in their lifetimes, hinting at their eventual supernova explosions. These insights are helping astronomers map out the life cycles of the most massive stars, which, until now, were mostly a mystery. One of the most exciting aspects of Webb's findings is the way these massive stars interact with each other. Unlike smaller stars, the hypergiants in Westerlund 1 tend to form in tightly packed regions, leading to extreme gravitational dynamics. This causes stellar winds and collisions, creating shock waves that ripple through the surrounding space. Such conditions are not just rare, but are key to understanding how elements like carbon and oxygen are scattered throughout the galaxy. These are the very building blocks of life as we know it. The discoveries in Westerlund have far-reaching implications. Massive stars play a pivotal role in seeding galaxies with heavy elements. By studying them in such detail, Webb is helping scientists refine their models of galactic evolution. Westerlund 1 offers a snapshot of how the Milky Way might have looked billions of years ago during its star-forming peak. It also raises questions about how such clusters contribute to black hole formation, another area ripe for exploration. This is just the beginning of what Webb can teach us. The telescope's unparalleled sensitivity will allow it to continue studying Westerlund 1 and similar clusters across the universe. Future observations aim to capture real-time changes in these stars, offering even deeper insights into their life cycles. Additionally, Webb is set to explore how these clusters influence the interstellar medium, potentially rewriting our understanding of star formation on a universal scale. Hypergiants are like the superstars of the cosmos, both in size and importance. These massive stars in Westerlund 1 generate intense stellar winds that scatter vast amounts of gas and dust across space. This material becomes the raw ingredients for new stars and planets. Webb's observations revealed that hypergiants act like cosmic gardeners, enriching their surroundings with heavier elements formed in their cores. These processes are crucial for the formation of solar systems like ours, reminding us of the interconnectedness of the universe. What makes Westerlund 1 unique isn't just its massive stars, it's the proximity of these stars to each other. This environment creates a stellar laboratory, allowing astronomers to observe phenomena that are rare or impossible to detect in isolation. For instance, Webb's data shows evidence of stellar collisions and mergers. These events are spectacularly violent, but also incredibly informative, offering glimpses into the physics of extreme gravity and energy transfer in the universe. Why is Webb so effective in studying clusters like Westerlund 1? The answer lies in its infrared capabilities. Infrared light can pass through the dense clouds of dust and gas that obscure visible light. By observing in this spectrum, Webb captures intricate details of star formation, energy transfer, and material ejection. This ability is a game changer, enabling discoveries in regions previously hidden from view, like the cores of massive clusters. Westerlund 1 is a treasure trove of information about the final stages of massive stars. Webb has captured data on how these stars shed their outer layers, forming beautiful and chaotic nebulae. These processes eventually lead to supernova explosions, dispersing heavy elements like iron and gold into space. Such elements are critical for building rocky planets and even life itself. Westerlund 1 offers a real-time look at the epic drama of stellar death. Massive stars don't just vanish after their spectacular supernova events, they leave behind exotic remnants. Westerlund 1 is likely home to neutron stars and black holes, the densest objects in the universe. Webb's observations are expected to help pinpoint these remnants, revealing their locations and interactions with their surroundings. This insight is vital for understanding gravitational waves, which are ripples in spacetime caused by extreme cosmic events. Studying Westerlund 1 isn't just about understanding our galaxy, it's also a window into the past. Clusters like this mimic conditions in the early universe when galaxies were forming at a rapid pace. Webb's findings suggest that star formation in these dense environments is more chaotic and dynamic than previously thought, offering clues about how galaxies like the Milky Way came into existence. Webb has provided detailed images of stellar winds, powerful streams of charged particles emitted by stars. These winds sculpt the cluster, creating bubbles and shock fronts in the surrounding gas. The intensity of these winds in Westerlund 1 is unlike anything seen in smaller star systems, showing just how influential massive stars are. This youthful age provides a unique opportunity to study the early stages of massive star evolution. Webb's findings suggest that the cluster is still in its formative phase, with ongoing processes that will determine its long-term fate. The heart of Westerlund 1 is densely packed with stars, making it one of the most extreme environments in the galaxy. Webb's ability to resolve individual stars in this chaotic region is a major breakthrough. By studying the central area, scientists hope to understand how these massive clusters remain gravitationally bound despite the immense forces at play. Clusters like Westerlund 1 don't exist in isolation. They play a crucial role in the broader ecosystem of the Milky Way. Webb's data shows how material expelled from the cluster is enriching the surrounding interstellar medium, providing the building blocks for future star formation in nearby regions. Findings from Westerlund 1 are influencing the design of future space telescopes and missions. Webb's success demonstrates the importance of infrared capabilities, inspiring scientists to develop even more advanced tools to explore the cosmos. The insights gained here will guide observations of other star clusters and galaxies. Although Westerlund 1 isn't a prime target for exoplanet studies, its discoveries have indirect implications for understanding planetary systems. The heavy elements produced by massive stars are essential for planet formation, including Earth-like worlds. By mapping these processes, Webb is contributing to our search for habitable planets. Ultimately, studying Westerlund 1 is about answering the big questions. Where do we come from? How does the universe work? Webb's observations are helping us piece together the cosmic puzzle, revealing how the stars and elements that make up our world came to be. It's a humbling reminder of our place in a vast and interconnected cosmos. Massive stars, like those in Westerlund 1, live fast and die young, while smaller stars, like our Sun, can burn for billions of years. The stars in this cluster consume their fuel at an extraordinary rate. Webb's data reveals the intensity of nuclear fusion in these giants, producing vast amounts of energy and heavy elements. Understanding their short lifespans helps scientists predict how and when they'll go supernova, shaping the cluster's future. Supernovae are not just spectacular, they are critical for the universe's evolution. Webb's insights into Westerlund 1 suggest that when these massive stars explode, they enrich the galaxy with elements necessary for planets, atmospheres, and life. These explosions also trigger the formation of new stars by compressing nearby gas clouds, demonstrating the cyclical nature of cosmic life. The immense mass of Westerlund 1 creates a unique gravitational environment. Stars within the cluster are in constant motion, their paths influenced by the cluster's overall gravitational pull and their neighbors' proximity. Webb's observations provide detailed models of these dynamics, helping scientists understand how such clusters remain stable over millions of years. Among the fascinating discoveries Webb is making in Westerlund 1 is the identification of protostars in their earliest stages of formation. These stellar embryos offer a glimpse into the birth process of massive stars. Observing their development is helping refine theories about the initial conditions required for forming such colossal celestial bodies. Magnetic fields play a significant role in star formation and evolution, particularly in a cluster as massive as Westerlund 1. Webb's instruments are detecting how these invisible forces shape the movement of gas and dust. By understanding these interactions, scientists can gain a clearer picture of the complex forces at work in star-forming regions. Clusters like Westerlund 1 don't last forever. As stars die and material is ejected, the cluster loses mass, potentially leading to its dispersal. Webb's data is helping scientists predict how long Westerlund 1 will remain intact. This information is essential for understanding the life cycles of star clusters and their eventual contributions to the galaxy. Dust might seem insignificant, but in space, it's a key player. The dense dust clouds around Westerlund 1 are rich in elements crucial for planet formation. Webb's ability to study this dust in unprecedented detail is revealing its composition and role in the cluster's evolution. This knowledge is vital for understanding how the raw materials of life are distributed across the galaxy. Westerlund 1 is unique, but it's not the only cluster of massive stars. Comparing it to other clusters, like the Tarantula Nebula's star-forming regions, helps scientists identify patterns and differences in star formation. Webb's observations are providing a comparative database, enhancing our understanding of the universe's diversity. Feedback loops occur when the energy and material ejected by massive stars influence the formation of new stars. In Westerlund 1, these processes are particularly intense. Welcome to Blessovia Science TV, where we take you on an exhilarating journey through the cosmos and unravel the mysteries of science. We are excited to offer you the opportunity to become a valued member of our ever-growing community of cosmic enthusiasts and knowledge seekers. Exclusive access to cosmic content. As a member of Blessovia Science TV, you will gain exclusive access to a treasure trove of cosmic content, including documentaries, interviews with leading scientists, space missions updates, and awe-inspiring visualizations of the universe, live Q, and sessions with experts. Your membership will grant you the chance to participate in live Q and sessions with renowned scientists, astronomers, and space explorers. Get your burning questions answered by those who push the boundaries of human knowledge. Embark on a journey that spans the cosmos and join us in unraveling the secrets of the universe. Become a Blessovia Science TV member today, and together we will reach for the stars. Thanks for watching. Subscribe, like, and share. Don't forget to leave your comment.